Okay, hi, good morning, everyone. So it's week 7. I hope you had a good recess week. And this week we'll be having our midterms, right? So this tutorial is just like going through questions I prepared for the class. Um, so yeah, so okay, we have started recording. So okay, these are several of the questions that I prepared. So first of all, I'll go through the 2D peak finding in linear time. We covered a question, exactly the same question in tutorial, but we solved it in m log n time. Okay, so we try to push it down to om plus n. Okay, then question 2, expected number of inversions. This was actually a question I prepared last semester, but it turns out that that prof kind of like coincidentally used a similar question for the assignment. So I hope you have seen it. Okay, so if you don't see the link, let's see whether you can figure it out later. Okay, and the third question is something new, like I introduced to the to this semester's questions for the tutorial. So maybe you haven't seen it before. Okay, but it's inspired by one of the tutorial questions on peak finding. Okay, so I have 2 extra questions, but I think I won't hold people back if in case like they don't want to listen to it. But what I plan to do is that, you know, if people are not answering it, maybe I'll just go through it in the video anyway. Okay, so just very chill. If you have questions about the midterm, you can ask me later. Okay, so again, like quick administrative matters. Midterms is this Thursday for you guys during lecture time. Okay, and week 1 to week 6 content should be examinable. And just in case, right, like for those watching this video wondering, expecting me to go through the fingerprinting material, it's not in this tutorial. It's I already uploaded a separate video. It's up in the announcement somewhere. So check out the announcement there, and even the answers are already uploaded to Luminous. There should be a midterm logistics files as well. So please do check it out. Maybe I'll just remind you to, like, because you're writing on pen and paper, so do try your application and see if you are able to scan and upload properly. Okay, just a gentle reminder. Okay, so let's just begin it proper. All right, so the first question is about 2D peak finding in linear time. So let's recap a bit, like what the question is about, how we solved it last time. Okay, so given the 2D array, right, a 2-dimensional array of size m by n columns, okay, we see that an entry aij is a peak if it's greater than or equal to its adjacent neighbors. Okay, and in this question, it doesn't have to be a global peak, right? So it doesn't have to be like the tallest peak ever in the entire array. It can be like the number 8 over here. It's just bigger than its adjacent neighbors. So all you care about is that it's bigger than its adjacent neighbors. Okay, so recap a bit, like how did we solve it last time in the tutorial? Okay, so for om log n solution, okay, so the key property here is this: if aij is the largest element in column j, and we assume, right, this is the largest element, say this is the largest element, assume that the neighbor to its right is bigger, right? So what happened if, in case you found a max in the column, you see that, oh, turns out this 50 is not a peak, right? It must have been because like one of its neighbors is higher. Okay, so you argue that in this subarray, right, in this subarray where you found the taller neighbor, right, any peak that is the largest element in the column is also a peak in the entire array. So in this subarray, if you found a peak that is also the largest element in the column, right, it must be the peak in the entire array, right? So why? So, well, recall that if it's this region, the j plus 2, it's very trivial because it's kind of like how whether this guy is peak or not, right? It's not affected by whatever's on the left in the diagram. Okay, so this part is very intuitive because you know, it's okay, yeah, I think it's very intuitive. I don't know what else to add. Okay, but the part over here is a potential problem. Okay, we need to do a bit more work. And why is that? Because if you add back to the part of this region that's removed, right? So the concern here is that if you found an element, like let's say this guy is the max, right? It was 100, right? What we don't know is the information about this guy. We decided that 100 was a peak purely based on this subarray, right? So what happens if the neighbor here is something higher, right? Maybe it's like 1000. Could it be that it can ever be 1000? Okay, the answer is of course no. You have seen this in the tutorial, but again, like this was the concern last time, right? Like the intuition I tried to say is that, you know, you're kind of like the best fish in your own pond, but does that mean that you're still the best fish in the ocean? Okay, so this is the work that I said we need to do more last time. Okay, and let's recall like the rough argument very quickly again. What we did, right? So we label these elements like A, B, C, D, where D is the peak in this subarray. That is also the largest element in the column. Okay, so recall like D is greater than C. D is greater than C because this is what we output. We claim that D is the largest, is the peak that is also the largest element in the column. So D is greater than C, okay, greater than equals to. Then C is greater than B because of our argument, like our assumption that we went to the right, we recurse to the right because of this C here is at least B, right? That was why we recursed to this subarray in the first place. And well, A is greater than B because A is the largest element in column J. Okay, so sorry. B is the largest element in column J. So though this guy B is greater than A, like this was our choice of the largest element in the column. Okay, so thus by following this series of inequalities, we see that D is greater than C, greater than B, greater than A. So we have D greater than A. Okay, so this is something you've seen before. I understand maybe some people don't remember the argument, but hopefully this refreshes your memory a little bit, okay, about how we argued about this. This was the algorithm we had. Okay, so the base case, we just return the max in the column, right? We return the maximum in the column, and otherwise we try to see the maximum of the middle column, try to find the maximum of the middle column, and let's say if that guy is a peak, then it's fine, just return. But otherwise, we recurse to the side, only to the side that we need to recurse on, like the reason why we weren't a peak. Okay, so all right, so that is the question setup. If anyone needs me to like refresh a bit more, like repeat, please do let me know, like maybe like private PM me or something. But I really hope that this argument you have seen before and you kind of like remember your memory in a bit. The question is like, let's solve this in OM plus n time, because last time we solved it in OM log n, right? OM log n. That was how we solved it last time. That's the argument. By recursing to one side, we solve it in OM log n time. So can we try to solve this even faster in OM plus n time? Okay, I won't really stop to like let people think, but if you're watching the video, you can pause and think again. This is also an answer in the practice set. So let me just put it in slides form, you know, like explaining a bit further why the design is as such. Okay, so well, here's the idea, right? So we try to divide the array by 2 to give us a better solution, right? Initially, we just search naively the entire array. The very, very nice solution is to search the entire array. But we try to improve upon it by dividing by the column and then recurse to 1/2. Okay, so well, that improve it by 1 dimension, kinda like from OMN. The nice solution is OMN. The n brings down to log n, right? Becomes OM log n. So here's the idea: like, can we divide even further, right? Divide even further, meaning that we only divided by columns earlier. Okay, but let's try to divide by both rows and column. Okay, so we don't just divide by 1 dimension, we divide by 2 dimensions. Okay, to get something like this. To get something like this, so you kind of like create a cross, like a plus here, right? So what you do is you find the max, right, in the yellow plus. If it's a peak, then you just return it, very easy. But otherwise, you recurse on the larger side. Okay, it's a very simple follow-up to what we did earlier. Earlier, we just divide on 1 column, find the max, and then recurse, right? But this time, what we do is we make a plus. We divide by 2 dimensions. Then we recurse on. If we don't find a peak, we recurse on the side that gives on the subarray that prevented you from being a peak. Okay, so well. First of all, like, does this idea work, right? So it's a very intuitive follow-up, but unfortunately, it doesn't actually work. Like, not fully. It's very close to being working, but it doesn't actually work. Why? Let me show you why. So let's say, right, the element 10 is the max in the plus here, right? Like this guy is the max. So everything else, you can just imagine everything else is 0, if that helps. Okay, so it's the max, but it's not a peak. Why is this guy not a peak? Because it was blocked by this 11. This 11 blocked it from being a peak. So therefore, like our intuition says that, you know, we recurse on this larger side, right? So we recurse on this sub matrix, recurse on this sub matrix here. Okay, so we recurse on this sub matrix here, and then let's create another plus, right, by our recursive algorithm. So I couldn't draw a square that is large enough to fit a properly placed plus, but I hope this kind of like illustrates, you know, like let's say we round down the center, right? So we create another plus by recursive algorithm. And then what we do is by our algorithm, excuse me. So in our algorithm, we find the max, right, in this plus. So let's say we found the max. The max is actually 8, right? In this sub matrix, it's actually 8. In this actually, it's 8. And then just by zooming in this sub matrix, you see that, oh, 8 versus 0 versus 0 versus 0. So 8 is a peak. This guy, the number 8 here, is a peak, right? In this sub matrix, in the red sub matrix that I highlighted. Okay. But this 8 in the sub matrix is not a peak in the overall matrix because of the number 9, right? Like, how could this be? Like previously it was fine, right? But this time it fails. So in the same analogy, this guy was the best fish in its own pond, but it's not the best fish in the entire ocean. Okay. So look, I mean, just convince yourself that this example, right, really shows that our algorithm will decide that 8 is the peak purely because it sees this region and it says that, oh, 8 is not a peak, right? It doesn't have access to whatever's outside because we only focus on this sub-array. But once you return that 8 is the peak in this array, in this sub-array, it doesn't mean that 8 is the peak in the entire sub-array. This region will prevent it from doing so. Okay, so you know, like this is why, and maybe like let's generalize a bit more what the fundamental problem is. The fundamental problem is that there's no relationship we establish between this 8 and 11. So we already claim like, oh, 8 is 9 is less than 10 is greater than 11. Then suddenly we just throw away this information, we don't use it anywhere, and like go along like our happy own way to create this plus without relating it to 11 in any way. So we didn't establish any relation between the number 11 and 8. So let's recall again, right? Like the original one in the tutorial, the simpler version, we needed this link. We need to follow this: B is greater than C, C is greater than B, B is greater than A, right? So ideally, we want something similar for this question as well. But what happened actually, if we only do a plus, is that here, right, our goal is we want D greater than C, C greater than B, B greater than A, right? Because that will allow us to say that D is greater than A, if that actually was a case. But what actually happened, right? Okay, so this is what we want. Okay, but what actually happened is that if we do only the plus, right? Notice how the plus here, it doesn't make any links about D and C. It's missing this link between D and C. Okay, it's missing this link between D and C, so we cannot make any guarantees about the relationship between D and A. That is the fundamental problem in this solution, the current solution. Okay. So like, are people following like the reason? Like, do you need me to repeat? I'll pause here. Like, if people are following, please give me like a thumbs up. If not, then I mean, I suppose maybe you might be focused on something else, but it's fine. If you want me to repeat, just PM me. But I see some thumbs up. Very few, but at least people are following. That's nice. So this is like the fundamental problem in our current design. Okay, so the idea is that we want to maintain a relationship between D and C. Like somehow we want to connect this D and C, right? So how to connect this D and C is by introducing borders, right? So rather than you just finding the max in a plus, right? You find the max in this like crosshair. I don't know how to pronounce it. Crosshair. I'm just gonna say crosshair. Okay. So you find this border, you include the borders, right? You include the borders, and the next recursive step will allow us to establish a relationship between C and D. Okay, so the square is a bit too small, but maybe if I were to redraw it, like imagine right now the 1, 2, 3, 4, 5, 1, 2. Okay, so maybe like C was over here, D was over here, right? So originally, if we only had the plus will only cover this region. Hey, sorry. Let me erase the D. Okay, originally, if we had the plus, it only covers this region, right? You say that D is the max, but it does not touch the C at all. But with the cross-share, right? With the cross-share, now that you add the borders, now you're able to maintain a relationship between C and D by the fact that C lies in the border. C lies in the border, so it's going to connect itself with anything in the border as well. Our concern is the border elements, so we want to link up the border elements together. So now with this cross-share, right, when we recurse, right, when we recurse and find the max, we are guaranteed that D is greater than C, because of the fact that we define this region and we want to find the maximum in this region, in this cross-share. Okay, so do people follow this? Like, does anyone need me to repeat? Like, again, give me a thumbs up. These are the two crucial observations and for us to solve the problem. Okay. Okay, nice. So I see thumbs up. Just one though, but I hope others are okay with it as well. Okay, so if you need me to repeat, let me know. So okay, now let's consider what's the time complexity, right? So that's actually the solution. So everything else, it follows the same guarantee. You can argue the same way that this subarray's peak will be the peak of the entire array, right? And really the crucial point is to maintain this relationship between C and D. Okay, so what's the time complexity? So, well, if you analyze the recurrence, it's gonna appear something like this: Tmn equals to Tm over 2 n over 2 plus Om plus n. Why Om plus n? Because it takes linear time for you to scan through the columns plus the rows, right? So that's Om plus n. Why m over 2? Because, you know, like the size of the, just, you know, like there's a bit more, like m over 2 minus 1, n over 2 minus 1, but for now, like for simplicity, let's just assume it divides by 2. That's the more crucial factor. This is like m over 2 out of, approximately m over 2 out of the entire m, right? And similar argument for n over 2. Okay, so, well, you know, this is a two-dimensional recurrence. We haven't really like learned how to properly solve it in lecture, but it's not that difficult to extend. So let's try to solve something similar, right? Tm equals to Tm over 2 plus Om. Okay, so if you try to expand the recurrence, okay, you try to expand the recurrence, you get, so focus on this region first, you get something like Cm plus Cm over 2 plus Cm over 4 all the way. Okay, and if you factor out the Cm, right? If you factor out the Cm, you notice that what you get here is the sum of GP, 1 plus half plus a quarter plus all the way, right? So here, just assume like it goes all the way to infinity. Like just assume like it goes all the way. And because sum of GP towards infinity is in the special case of the common ratio of the GP is less than 1, right? Here it is half. R equals to half. This is a special case where you can just say that this is bounded by a constant. The formula is like A over 1 minus R, right? So A is the first term. This is 1. So we have 1 minus half to get 2. Okay. Yes, 2. So this entire thing is bounded by 2, right? Or I mean, it's very much simpler to say like it's bounded by a constant, by O1. Okay, so this entire thing is Om, like this recurrence is Om. Okay, so this is if you try to solve it by expanding the recurrences, or maybe like if you imagine it's a recursion tree, like a linear tree. Okay, or you can always use master theorem for this simpler case. So let's recall like how do we do master theorem. Okay, so master theorem, again, there are three cases, right? I won't go through the entire three cases now, but typically what you care about is a recurrence in the form of Tn equals to ATn over B plus Fn. Then what you want to do is to compute n power log base BA. This is the first step to master theorem, typically, right? So here, n is log base, let me put another color, B is 2, A is 1, and this is because this is 1, and excuse me, and this is 2, right? So log base BA comes from over here, okay? And sorry, I put A here, but that should be 1. This is 1. Okay, so this means that this is n power 0 because log base 2 of 1 is 0. Okay, so well, this is kind of like a constant. Okay, and what you want to do is to compare this versus Fn. Right, so you want to compare this versus Fn, where Fn here is Om. In our case, it's Om. How does these two compare? There are typically three cases you want to compare. Like I think case 1, I forgot the ordering. I think case 1 is to show that Fn equals, this is case 1, n log base BA plus epsilon. Okay, correct me if I'm wrong. Okay, so I'm just trying to remember this from minus E, yeah, minus epsilon for some epsilon greater than 0. Case 3 is something like Fn equals to omega n log base BA plus epsilon. Okay, so this is case 3, and case 2 is there's the log factor to it, but I won't go through. But let's focus now on this, right? So this is 1, and Fn is this. Well, clearly that is clear. I hope it's clear that okay, wait. So something I conveniently wrongly placed here is I say n power log base BA. But in this recurrence, because our variable is m, right? Our variable is m, so these should be m. These are m. So if you would compare these two, you see that the m power log base BA, right, is, well, it's Fn is actually like omega of m power 0 plus some epsilon, right? You can think of it like, because this is Om, right? Something like Om. Then here, right, the epsilon can be just like maybe 0.5. It's actually omega of square root of m, right? So this falls under case 3 of master theorem, okay? And because this falls under case 3 of master theorem, of course you have to check what they say the regularity condition. So do check it out. I won't check it here. The conclusion of case 3 is that if this holds, then this implies that the runtime of the algorithm is Fm. Okay, so apologies, I mixed up the n and m a lot in this question, but I hope like you can mentally substitute them. But the conclusion is that Tm equals Fm, which is also Om in our case. Like this entire monologue about master theorem is not necessary, but you know, because it's pre-midterms, I thought I might also revise it a little bit for you. Okay, so this is time complexity for this particular recurrence. Okay, so we are not done. We are not done. If you didn't follow the entire discussion just now, revise master theorem and watch the video again later. Okay, so let's now solve this Tm over this mess over here. So I'm not sure if there's a way to do it by master theorem, but if you were to at least expand the recurrence, right? So similarly, right, here, right, we only expand Cm over 2, Cm over 4. But over here, right, what we can do is we just expand it together, like m plus n, m over 2 plus n over 2, and so on. Okay, I omit the constant here for simplicity, but if you do some rearranging, notice how m plus m over 2 plus m over 4 is the same thing as just now. It's going to form a GP with m as the factor, and it's going to form a GP with n as the factor. Okay, so if you factor out the m and you factor out the n, you again get the GP that's bounded by a constant, and you see that this is Om plus n. Okay, so hopefully the time complexity analysis is clear. By now, I really hope you should be familiar enough with some of GP and so on. Okay, so but if there are any questions, do let me know. So this is question 1. Okay, that took a while, but I hope the elaboration is giving you enough details to understand like the solutions in the non-assignment practice set. Okay, so I'm gonna just go on to the second question. If you didn't follow whatever I was talking about for the past 20 minutes, that's okay. We are gonna like change mode now to randomized analysis. Okay, so you can maybe like reset your mind a bit and let's try again. Okay, expected number of inversions. Again, this should be very familiar. It's almost identical to your assignment question, which also happens to be a past year midterm question. Last year, I think, 1 year ago. Okay, so here, right, you're given a permutation of the array which contains distinct elements 1 to n inclusive. So we define an inversion is such that if the index is I less than j, right? So intuitively, the element appears to the left, right? To the left, but the element itself, right, is greater than the element on the right. So for example, right? So if I have like 1, 3, 4, 2 here, right? So if I look at index I and j, right? This index over here and over here, A2 is 3 and A4 is 2, right? So this element 3 and 2, right? So 3 and 2, focus on 3 and 2, but the element to the left is greater than 3 is greater than 2. So this pair is an inversion. Okay. So similarly, if you look at element 3 and 4, right? So element at index 3 and 4, the elements itself are 4 and 2, right? The element to the left, which is 4, is greater than, so it's an inversion as well. Okay, so 1 and 4, for example. So at index 1 and index 3, right? The element itself are 1 and 4, but they do not form an inversion. Okay, so so given that you have the permutation occur uniformly at random, what is the expected number of inversions in the array? Okay, hopefully really like this really rings a bell. It's phrased slightly differently, but the analysis is identical. Okay, so since you have done the assignments and hopefully maybe you have visited the answer key as well. So yet again, the idea is to do indicator random variables. So if you're analyzing randomized algorithms, just try and take indicator random variables. Disclaimer is not always indicator random variables, right? So sometimes you can form it as like the sum of random variables that form geometric distribution, like coupon collector problem. Okay, but typically indicator random variables is like the go-to tool, at least for me. Okay, so again, this is the analysis pattern. Let me remind you again before the midterm. Remember, we want to identify the random variable that we want to count. Okay, we want to count, let's say x, and our goal is to find expected value of x. So again, express it as a sum of random variables, x smaller ones, x1 all the way to xn. Calculate the relevant probability so that you can get the expectation of all of these. Okay, get the expectation of all of these, and then you use the linearity of expectations, right, to get ex, because this is a sum of all ex plus 1 plus all the way to ex plus n. Okay, so this is the steps. Remember that. So recall, our goal is to find the expected number of inversions, right? We identify what we want to do. So x be the random variable representing the number of inversions. If we let xij be the indicator random variable, for the element at index I and j form an inversion. So now we describe the indicator random variable as a pair of elements. So as a pair of indices. Okay, so I and j form an inversion, and we want to sum it over all pairs of I and j. Okay, so the next thing we have to do is to calculate the probability of xij equals to 1. What does it mean that xij equals to 1? Remember, it's an indicator random variable. It means that the event happened. It means that the event element at index I and j form an inversion, right? So just focus on those two elements, see whether they form an inversion or not. And because this is an indicator random variable, you get the expectation for free. The probability itself is the expectation. So we can calculate EX by the linearity of expectations. Okay, so when is it that Xij equals to 1? Okay, so again, by the definition of Xij, when is AI greater than AJ, right? So that's the question. So what's the probability of this happening? So I believe that maybe a lot of people might have tried to brute force count everything. So that's fine. That's one way. But here's like kind of like the idea. The idea is that the permutation is uniformly distributed, right? So any permutation is equally likely. So if you just focus on the I and J, intuitively, either one of it is greater than or less than the other. So it only has to be the case that it's either AI greater than AJ, right? Element to the left is greater than element to the right, and the element to the left, or the element to the left is less than the element to the right, right? So they are equally likely to happen because it's a uniform distribution. The permutation is equally likely to happen. And well, we don't really care about the equality because the question says it's a distinct element. Okay, so intuitively, it's either left side greater than or left side smaller than. That's why this is half. Okay, and you can argue it by saying, you know, like permutation is uniformly distributed, so equal chance must be given. Okay, so well, all permutations, I mean, if you focus, okay, so if you just want to convince yourself that's really the case, this is the permutations of n equals to 3, all the possible permutations. And if you just focus on the first two elements, focus on the two indexes, notice that only forms like inversion half of the time, right? For a corresponding 2-1, a 1-2 appears. For a corresponding 2-3, a 3-2 appears. For a corresponding 3-1, a 3-1, 1-3 appears. So it's kind of like, you know, there's the counterpart to it, right? The reverse counterpart to it, intuitively. Okay, so this insight, I think, is what makes the analysis very simple. Okay, if you took a while to get this probability by counting everything, that's fine. I think that's a very intuitive first thought to go. First time I solved this question, I did something like that as well before realizing we can just apply this train of thought. Okay, so well, the next thing you do then, once you've identified the probability, is the same good analysis, right? Because this is linearity of expectations here, sum of all the indicator random variables. And then note that the probability of this happening is half. This is what we computed, right? And I hope you can recall that how many pairs are there, right? Such that I is less than J, right? It's n choose 2 pairs, right? There are n choose 2 pairs. And this is the value that you get, which is the same answer in the assignment. Okay, so anybody have any questions, right? So again, I'll pause here if anyone wants me to clarify something. If not, again, like just give me thumbs up like usual. Okay, very nice. People are thumbs upping. Great. So hopefully that refreshes your mind a bit on doing randomized analysis. So no question. If there are no questions, let me go on to the next one because this is slightly more interesting. Okay, expected number of peaks. So here, right, recall like the definition of a peak. So what happens is that you're given an array n of distinct integers from 1 to n. So you get a random permutation of this array, same like question 2 just now. Get a random permutation of the array. So we define AI to be a peak if AI is greater than its neighbor or neighbors, right? So all its neighbors. So for example, 3 here is a peak because its only neighbor is 1 and 3 is greater than 1. So this guy is a peak. This guy is a peak, right? Then 5. What's 5? 5 is a peak because, you know, it's greater than 1 and greater than 4. Okay, wait, let me redraw that. 5 is a peak because this is greater than, right? So this is the two inequality signs, but 5 is greater than 1 and 5 is greater than 4. So 5 are peaks. So what is the expected number of peaks in the random permutation of the array? Okay, so maybe I'm not sure if you have tried this before, but try maybe like give it a bit of quick thought, right? So I'll give you like a minute or two and try to fill in archipelago if you're in, but if not, just give it a quick thought. Okay. So if you don't know, just say you don't know in archipelago, but maybe like just put in whatever ideas that you have. So let's resume at maybe 11:40. Okay, to the person who just put I don't know in archipelago, so there's only one so far. Maybe you can PM me and like what's your first thought? You know, like what should you do for this question? It's okay you don't get the final answer, but maybe just tell me if you know at least what you think you should do. Okay, sorry, I was answering some PMs, that's why I was a bit quiet. Let me see the question. Okay. Okay, yeah, I see some decent attempts. Over 4. Okay, so let me try and answer this. So let's go through it. 3xi 2/n times half plus. Okay, so let me go through it and see whether this is okay, so let me go through it first. Again, like again and again, right? Again, we use indicator random variables. So the idea here is really indicator random variables. So again, our goal is expected number of peaks. So we let that be the random variable. We let that be the random variable, and let xi be the indicator random variable for the event that element at index I is a peak. Okay, and the x is simply the sum over all the xi, right? So the next thing we have to do is to compute the probability that element at index I is a peak, xi equals to 1, to get expectation of xi. Okay, so if you manage to at least get to this step, I'm happy. Okay, because really the hard part is really computing this probability, I feel. Okay, so xi equals to 1 when element at index I is a peak. When does this happen? Okay, so notice here, right, the tricky part about this question and what I like actually is how there are two cases. So the case one is that there's an edge element to all the way to the left. You only need to compare with one neighbor, right? So what about the non-edge elements? You need to compare it with two neighbors to know that here, right, on case one, to know that whether the element index 1 is a peak, one indexing, okay, whether it's a peak, you only need to compare to its direct neighbor, to the right or to the left, depending on like whether you are which end you are talking about. Okay, but on the case 2, where you are the non-edge elements, you need to compare with two neighbors, either to the left or to the both to the right and to the left. Okay, so it's a case-by-case basis. What I kind of like about this question is that the probability is not the same throughout. You need to break it down a bit further. Okay, so what's the probability of the edge elements? You only need like if xi is an edge element specific for I equals to 1 and I equals to n, basically the two n's, what's the probability of xi being 1? Okay, so hopefully you can see that this is identical, almost identical to the previous question, in the sense that it's half. Half because you only focus on these two elements, right? Focus on these two elements, and because every permutation is equally likely, it's either that this element is greater or it's smaller. You can also argue the same for the other edge elements, right? So the probability is half for both. Okay, so if you get to this far, I'm extra happy. Okay, the other one is maybe the trickier one. Okay, so now non-edge elements. Now we need to compare with two neighbors, right? So we need to compare with two neighbors. So what's the probability of this happening? Okay, so now let us study, right? Because if you have this array, right? Like we say elements 1, 4, 5. What are all the possibilities? You just focus on this subarray. What are all the possibilities of the permutation, right? So it's like 1, 4, 5. It's 1, 5, 4. It's 4, 4, 1, 5, 4, 5, 1, 5, 1, 4, and 5, 4, 1. These are all the possibilities, right? All the permutations, basically. All the permutations happen, and each of them have an equal probability of happening, right? Because the permutation, all permutation occur equally likely. So therefore, like this, every of these 6 permutations also have equal probability of happening. Okay. So if I were to generalize, right? So it's this is actually like the same thing as what I put here. It's just like I put it in general form, AI, AJ, AK, right? So there are 6 cases, and each permutation is equally likely. 6 cases because 3 factorial. 3 factorial being the number of permutation of 3 elements. Okay, what do we care about? When is it that element AI is the peak? Right? Element AI is the peak if it's greater than both element to the left and to the right. So it's actually these 2 cases where AI is the greater of the 2. We don't really care whether the element to the left is greater than element to the right. But okay, so what I mean is that we don't really care if this is 1, 5, 4 or this is 4, 5, 1. Both cases, 5 stays as a peak. So we only care about these 2 cases. We only care about these 2 cases. And this is the probability that the AI is the peak. So 2 out of the 6 cases, it gives us a peak for the non-edge elements. So the probability that this guy here in the center is a peak, right? Or the non-edge elements is a peak is 1/3, because every permutation is equally likely. Okay, so is this reasoning clear? Right, it's a bit tricky, but it's a generalization of what happens if you consider. In the earlier question, we consider pairs, but here we consider triplets. And we consider triplets by considering all permutations of these triplets and see which case do we belong to, like which case do we care about. Okay, so this can be generalized even further if you want like find quadruplets of elements and some properties of quadruplets, right? But any questions about this? Like, can you give me a thumbs up, especially those who answered in Archipelago? If you have questions, do let me know. Okay, I see several answers in Archipelago actually have over 4. I wonder where the over 4 came from. Maybe you can like tell me separately. But let me just go on with this first. So probability of now we have 2 probabilities and 2 cases. So to do the analysis, we break down the random variable. We break down into 2 cases. Case 1 is the edge elements, right? The case where the peak, we care about the index at the edge, at the borders, right? And the others are the index at the non-edge elements, right? So I skip a lot of the linear expectations because I think you're very familiar with that by now. Okay, so this 2 probability is half and half. So these 2 are both half by our earlier calculation. And this one is 1/3. This one is 1/3. Okay. So the n-2 comes from the fact that we have n elements, right? We have n elements and we exclude the last 2 edges. So this is n-2. That's where the n-2 come from. Okay. So in total, n minus 2 over 3 plus 1 is the answer. Like this is me just adding up this together. Okay, so I think this question is really cool, like in the fact that it's a bit different from usual because we need to divide by cases, but it tells you like how nice indicator random variables can be, because you just need to consider different cases, and even if they are different, and even if they are dependent, right? If they are dependent, then it's still fine. Okay. So yeah. So this is the end of the tutorial. Like this is the final answer. I actually verified. I actually wrote a program to verify that really expected number of peaks is really this. I wrote the program by outputting all the possible permutations, iterating through like the total peaks, and then finding the total number of peaks divided by the number of permutations, and I verified at least up to n equals to 12, because it's fine, you know. N equals to 12 took me 20 minutes to run the program. 12 factorial is super huge. Yeah. So that's the end. Funny story about this question is that actually a student emailed me about this particular question just for fun after the peak finding tutorial. He was just curious, like, oh, what if we do randomized algorithm for this question? Then I solved this over like Chinese New Year reunion dinner. Like I was queuing for food, then I was thinking about this question. then during that I was like, oh, we can do this. Yeah, so that's the story behind this question. Let me share the slides in Zoom chat. Someone actually told me what he thinks about why there's the quarter. Okay, so link. Okay, so so I think the argument that so the argument that one person made is that, you know, this is element index I, right? And this element J and element K. I think what he's thinking is that we focus on two cases, right? So we break it even further by saying like, oh, probability of AI being a peak is equals to probability that AI greater than AJ, and probability of AI greater than AK. Like this is the definition of a peak, right? Then the calculation is done for him, right? Or for some of you, I believe, right? By separating these two. So let's say this is event E1 and this is event E2. So you say that the probability that AI is a peak is by multiplying the two probabilities together. EI times probability of E2. And you know that separately this is half and this is half. And I think that's how you get a quarter, I believe, right? So the problem with this argument, right? Someone actually, now that I recall, like someone tried doing this, is that from here to here, right? This is not like this is not a legal separation, because the event that EI happens is dependent with, event that E2 happens is dependent on E1. They are not independent events. You can only separate the two if they're independent events. But here, right, once you know that EI is greater than like 3 is maybe like something like this, once you know this, K will kind of depend on whatever value you reveal here. It's kind of dependent on that. So once you know that EI happens, basically like we know that 3 is greater than 2, it gives you a bit more information, right? To deduce what K kind of like, what's the probability of this happening. So they are dependent events, so you cannot just multiply the two together like that. Okay, so I hope this kind of explains, at least to those people who put like a quarter, which I believe like might be the reason why you think so. I think it's very close answers, right? I think the one proposed answer was n minus 2 over 4 plus 1, whereas the actual answer was this is over 3. So yep. Hope this clarifies. Let me undo that so that all the annotation is there. Yeah, so that's the end of the tutorial. If you want to stay back, I actually have like some extra questions which you can try in if you see the slides. I will maybe like talk through it in the video at least. So even if everyone leaves, I'll just put it in the video. Okay, so yeah. Okay, I kind of revealed the question in speaker notes, so please pretend the speaker notes don't exist. Yeah, and I hope it clarifies to those who attempted at least. Okay, let me check if there are any questions regarding midterms. Yeah, okay, so I think I answered the questions in Archipelago also. So yeah, all the best for your midterms, guys. Okay. Okay, so a question from a PM. Can you show the conversion from probability x equals to 1 to expectations? So I assume x is an indicator random variable. Is that right? Yes. Okay. So let me question 3. Oh, I see. So okay. So okay. So probability of xi, right? Because xi is an indicator random variable, this must mean the expectation of xi is also equals to 1 over 3 for I equals to 2 to n minus 2. Right? Okay, no problem, guys. So do you agree with me about this point? This is an indicator random variable. Unless you want me to derive how did I say that it's equal? Is the question about okay, so you're confused about this part. So for this question, I skip a lot of steps, but how I do it is that if I were to properly do it, it's going to be probability of x1 plus xn plus summation I equals to 2 to n minus 2 of xi, right? And by linearity of expectations, we get to this part over here. Okay, so that part I hope is clear. That was too fast. I undo first. So I break it down the x1, xn, and summation like this, and we break it down to by linearity of expectations. Okay, so from here to here, right, the missing step is by saying like this is actually probability of x1 being 1 plus probability of xn equals to 1 plus summation of probability of xi being 1. Okay, you got it. Did I misunderstand your question? Or now you get it already? Okay, great. Yeah. So this is the missing step that I should have added, but because like there's a lot of repetition, like we have done this so many times, I decided to omit the details, but maybe I shouldn't have, since you're asking me this, right? So you're wondering if you need to do 2 over n due to only 2 times we select h out of n elements. Is it this case over here? Like 2 over n comes from like the random choice of the probability. Yep. Okay, so you think no need in this case. Yeah, because I separate out explicitly. Okay, cool. No problem. Okay. Any other questions? If not, then let me just, like, for the sake of the video, go through these questions. Okay. Extra question 1 again is a simple practice of indicator random variable. Okay. So okay. So let me go through this. First, the question says that, like I'm a TA, right? So this is an online class. Okay, it doesn't apply for the physical class, but let's say I have n students, and then I want to discuss the approach to tutorial questions, and I open up m breakout rooms. So how I do it is that I assign uniformly at random each student to one of the m breakout rooms. So I look at student 1. Let me roll a dice, an m-sided dice, and choose where you should go. One of the m places, right? So what is the expected number of students in a breakout room for a specific breakout room? Okay, so let's focus on the IF breakout room, right? IF breakout room. So here the argument applies to all the m breakout rooms. So here I just fix a general breakout room. So the indicator random variable here, let xj be IRV for J of student to go to IF breakout room. IF breakout room. And if you don't like I and J, like you can just imagine like you fix a number, like maybe this is 3 to the third breakout, or maybe make it 4 so that I don't have to fix the grammar. 4th breakout room. Okay, so what's the probability of XJ happening? Well, there are M breakout rooms, so probability of XJ happening should be 1 over M. Right? So for that student, I randomly choose one of the M breakout rooms. Okay, I choose one of the M breakout rooms. So the probability of that breakout room that I want, right, the 4th breakout room to be chosen is 1 over M. So you get probability of XJ equals to 1 being 1 over M. Okay, so the next thing you do is how many XJs do you have? Like X equals to what? Right? X equals to the summation of all the way, right? There are n of such things. So the notation is a bit sloppy, plus all the way to xn. So there are n indicator random variables. Okay, so I'm just gonna skip steps because again, this is really things we have done, but the expected value of this entire thing, right, is, well, by linearity of expectation, you probably know by now, it's just substitute 1 over m inside, and then you times n over m. So you get capital N. So in total, the answer should be n over m. Okay, and that is the answer in my speaker notes, n over m. Okay, so simple exercise, because more exercises are always nice to reassure your knowledge, right, on it. Okay, so question 2. So if there are any questions, just stop me. So there are only so few of you. I think I can manage with like you just randomly stopping. Okay, so cover time of a complete graph. Now this question is slightly more interesting to me, right? So what happens is that you're given an undirected complete graph, right? So let's say complete graph of 5 nodes. So recall complete graph is all the edges are present. So you have 5 nodes. These are all the edges, right? Starting from a node, randomly choose one of its neighbors to visit. So it doesn't matter which node you choose from. Maybe you can imagine like you choose one of the nodes randomly. Randomly choose one of its neighbors to visit, right? So here, right, let's say we choose this node. It can go to anywhere. It can go to here, it can go to here, it can go to here, it can go to here. There are 4 possibilities for it to go, right? Go back. So this is called a step, right? We'll keep repeating this process of choosing a neighbor to visit, going from node to node. But take note, right? It can revisit a node that has been visited. It means here that if you go from this node, let's call it A and let's call it B, you can go from A to B and go back from B to A. That's fine. It's not prevented here. Okay? It's not prevented here. A to B, B to A is not prevented. So we say that cover time of a graph is defined as the number of steps. How many of this process, the steps you make to visit all the nodes in the graph, which includes the step to visit the first node in the graph. Okay. So what is the expected cover time, right, for this particular graph, complete graph Kn? Okay. So I'm just gonna like maybe leave it like a minute for at least those who are still here, like to just like imagine, you know, if you have any questions, let me know. Okay. If not, then I'll go through it. Okay. Okay. So the answer to this question, okay, so I'll go through it now. The answer to this question is, you can just say one word. Okay, maybe not one word, like maybe a sentence explaining that one phrase, and it's actually the exact same problem. So this problem, I argue you have seen it before. I mean, if you attend all the tutorials, you have seen it before in the tutorial. You can reduce this problem to something that you have seen before. Okay? That problem is called the coupon collector problem. Okay? So the coupon collector problem says that you randomly choose a coupon with replacement, right? Until you visit all the possible, you get all the possible coupons. If you think carefully about this question, you can imagine that the coupon, so let me write it down. Coupon is the nodes. Choosing with replacement is basically like taking a step, like take a step to go to another node, take a step to go to another node. Another node. Okay, so basically it's almost identical in the sense that, you know, here the coupon is the nodes, right? And our goal is to get to all the nodes, visit all the nodes. And in coupon collector, you potentially get back the same coupon. And similarly here, you potentially get back the same node, like something that you have seen before, right? So it's identical. So the analysis is almost identical as well. So expected cover time, just like the coupon collector problem, is theta n log n. This follows from the coupon collector analysis. If you forgot how to analyze, you can go back to the corresponding slides. I think it's in week 5. I believe you should be in week 5. Okay, so yeah, this is the answer. Like, expected cover time is theta n log n by the coupon collector problem, like by defining this. Maybe there are small technical details, right? So in coupon collector problem, if you choose coupon 1, but you can in the next round you can get back the same coupon 1 like right after. Like the key point, the keyword here is right after. But here, right, unless I allow self edges, maybe if you're at node A, right, if you're at node A, there's no way you can get back the same node A. Maybe you have to visit the neighbor first before getting the node A. So sure, like this might be a technical detail. Unless I allow a self loop, then it's the analysis is not exactly the same, but it's very similar. It's very similar, just replace the probability slightly. So instead of like over n, like I think the analysis of coupon collector, it should be an over n somewhere. You change it to like over n minus 1. And this minus 1 doesn't really hurt the analysis. It's still theta n log n. Okay, so this is the extra question 2. It looks complicated, but if you think about it carefully, it's very similar to the coupon collector problem. Okay, so that concludes like fully this extra bonus section. Thanks a lot for staying back to listen. Once again, like maybe I'll just wrap up maybe I'll give you a chance if you have any questions before I wrap up and close the video.
Hi, Christian.
Oh.
Yeah, so for this question, right, it didn't say we can visit the same node again. So shouldn't it be n over n minus 1 instead of over n?
Yeah, exactly. That's what I was saying before. So if you're at node A, you don't visit back the same thing, right?
Yeah.
You cannot visit back the same thing unless I allow self loops. So what I'm trying to say is that sure, it's not 1 over n, but you're right. Maybe it's like 1 over n minus 1 or whatever the denominator is, right? So you're right that it should be over n minus 1. But if you try to do the analysis, right, it's still gonna be theta n log n, because basically the minus 1 doesn't really hurt. Like you can imagine maybe the result would be something like theta n minus 1 log of n minus 1. But I mean, this is still okay. This is not the actual answer. I have to carefully do the analysis. But the point is that minus 1 doesn't really hurt that much in the grand scheme of things. It's still theta n log n. Yeah, but you're right there. But you're right there that if you want to do the analysis carefully, you have to do the like over n minus 1. But if you repeat the entire analysis with over n minus 1, the final result shouldn't change too much. It should be theta n log n still.
Yep, got it. Thanks.
So it's like same but different. Okay. Any other questions? Okay. If not, then I think I'll conclude the recording. So I covered all the questions that I wanted to cover for before midterms. So if there's anything, just let me know. Like you can PM me. Anyway, try not to PM me for now because I have exams on Tuesday and Friday as well. But ask in the group and let's see if someone can help answer. Okay, so I'm gonna conclude the recording. If you have any questions, just let me know. So thanks a lot and all the best for your midterms.